robotics, I can confirm that. Yeah, his algorithms that he developed for his drones, they are even used by NASA. Also one of the very famous things he did, and I'm sure we will see that, is he even was beating the human world champion in drone flying with his autonomous drones. So his research got him many awards, among them just recently the Technical Field Award of IEEE. He also has an ERC Consolidator grant and many best paper awards, and his research was also published in Nature. He also has several startups, and I do now not want to take any more of your time, and I'm really looking forward to your talk. Thank you, Davide.
Thanks a lot, Kadia, for the nice introduction. I'm a roboticist with a computer vision background. So I usually don't attend control conferences. I think this year it's been the first time that I've been to several control conferences, but I'm very excited to be here, and I would like to thank the organizers to give me the opportunity to come and present our work, because of course for drone navigation we need control, and we are using a lot of your algorithms, so it was nice to see and meet the people behind the algorithms we've been using and see their face. So, but also that means I feel very intimidated, because of course you may also ask a lot of theoretical questions, and of course I don't know how I'm going to react, but that's also the reason why I'm here to get your feedback, most importantly. So I'm going to talk about vision-based agile robotics, but let me motivate this to show you what Kadia talked about. So last summer we organized the first human versus AI drone race, and I show you the result of that, and then I'm going to talk also about that.
That is beautiful. One day, I dream I can achieve that. Damn!
That's not human, man.
Insanity. I don't even know what I didn't want me to see that in person. One day, I dream I can achieve that. Damn!
So I always feel shivers when I show this video, because it was a lot of work. What you saw in this video was the conclusion of 15 years of research and work. A lot of NPC involved, a lot of optimal control, a lot of RL, and then back to NPC. This was vision-based. So this, the main narrative of this talk is how we can incorporate vision for agile, vision-based navigation. Because we need onboard perception to achieve true autonomy without GPS, without external motion capture systems. So let's rewind the time. Why do we need perception? It seems obvious, but let's see how perception has influenced the last 10 years of robotics. What you see on the left is a long exposure picture of a Roomba vacuum cleaner, the most sold robot after drones, that until 2018 would take 20 minutes to clean a 20 square meter bedroom. In 2018, Roomba released a new version of their vacuum cleaner that now would take only 5 minutes. As you can see, the difference is that now it can plan trajectories and can follow those trajectories precisely. So the robot became finally more productive. What made this possible? Perception. They added a camera and a computer that was computing SLAM, simultaneous localization and mapping. Is it more productive than humans? No. I take around 1 minute to vacuum my 20 square meter bedroom, so there is still a lot of work to make them competitive. And that's why they only sold 40 million and no more. Let's see another application where perception made the difference. We have all certainly watched this video from Boston Dynamics Atlas doing parkour. And what made this possible is perception. The robot uses 4 cameras that are triangulating points and building a volumetric map of the environment and feeding this to a model predictive controller that predicts the next footsteps. Where else has perception made a difference? On Mars. For the first time, NASA was able to have an autonomous robot operating on another planet. Yes, I'm saying that for the first time, because the rovers that NASA sent before were actually teleoperated from Earth. You cannot teleoperate a drone. You need the decisions at 100 Hertz. So this was the first robot to be fully autonomous. And it used a single onboard camera and an onboard computer. So what we see from these videos, and I hope I convince you, is that computer vision is making mobile robots autonomous, but humans are still preferred in most applications. Look around. Do you see any robots? No. Why? Because current robots are far from human performance in agility, versatility, robustness. And that's why, we still don't have autonomous cars that were promised in 1970s. Because to build an AI that can beat humans is very, very, very difficult. Now, I could work on many types of robotic platforms, and there are many robotic platforms. 15 years ago, I chose to work on drones, not because they are cool, but because of the research challenges that they raise. Because, in fact, the drone is one of the few robot types that without seeing, it cannot even hover stably in the air. Because a drone, a quadcopter drone specifically, is an unstable system. It behaves like an inverted pendulum. Just hovering a drone means it's like trying to balance yourself on the toes of your feet. And as you know, doing it blindly, it's impossible. You will eventually fall. So you need to open your eyes, fixate at least a single point in order to stabilize. If you don't do that, the drone will crash. Now, what you will also see in this presentation is that perception and action are strongly coupled. Again, the drone is one of the few robot types in which you see this coupling between perception and control. What is the dream of robotics? To build agents that one day can be more productive than humans. So what is the dream of people working on flying robotics? Is to build algorithms, autopilots, that can fly drones better than humans. What you see here is not an autonomous drone. It's a drone operated by a human pilot. How do human pilots operate drones? Vision-based. They put a camera on board that transmits the video feed to the goggles, and then a human brain computes the control commands and sends them to the joystick. When we started working on agile drone navigation, we thought that humans were better than machines because they were faster. And we were significantly wrong. Humans are actually super slow. In this paper, we analyzed 20 expert human pilots. And what we found was astonishing. The reaction time of expert human pilots is 250 milliseconds. By comparison, the ones of car expert pilots is 180 milliseconds. So a quarter of a second is spent in analyzing the images and sending the control commands to the fingers. By contrast, our autonomous algorithms take only 20 milliseconds, so they are 10 times faster. So how is it possible that humans beat machines in everything today? It's not because they're fast. It's because they can make better decisions in complex situations. Think about autonomous driving. You know how many accidents we have, humans? 1 every 100 million kilometers. Most of us, hopefully, will never have an accident. So it's very, very difficult to operate machines autonomously, to achieve the level of robustness of humans. But you may wonder, why do we need agile drones? So agile means fast, but also means that they're able to change the direction of speed very quickly. Why do we need agile drones? Why do we need agile autonomy? Actually, for a practical reason. Drones can only fly for half an hour. I'm talking about multi-copter drones. But if you can fly a drone faster, it can fly longer distances. In fact, counterintuitively, a drone consumes more power in hovering than in forward flight. But there is, of course, a limit. So what you see in this plot is a paper we published a few years ago where we plot on the vertical axis the range in kilometers that a drone can reach before running out of battery. And on the x-axis, the flight speed in meters per second. As you can see, the faster you fly, the farther you go. This plot is for a DJI Mavic drone, the most sold drone. So at the optimal speed of 6 meters per second, you reach the maximum range of 3.5 kilometers. But what happens if you go faster than the optimal speed? Then now you encounter more air drag, and it's no longer convenient to fly fast. Now, interestingly, when you look at the state-of-the-art commercial drones, none of them is flying at the optimal speed. If you don't know these companies, they are the 3 world-leading drone companies. The companies that have sold most robots. The drone is the most sold mobile robot, even before vacuum cleaners. And they fly at less than 1/3 of the optimal speed. But we know that one day they will be able to do that. Why? Because if you want to adopt robots, they have to be more productive than humans. And they're not even autonomous, they are teleoperated. How good are human pilots? Well, human pilots are so fast that typically, when, for example, they compete in competitions, they are not even optimizing for range, they're rather optimizing for chances to win a race. But some years ago, in my lab, we thought that if we want to push the limits on research, maybe we should work on something that is appearing unachievable, with the hope that the research results towards something that is unachievable could be applied to then fly drones at the optimal speed. Also with the hope that these algorithms can also be applied to many other domains like cars and other robots, space robots and so on. So agile autonomy is important for drone navigation, and it will have an impact in different fields. Not only search and rescue, where obviously you want to inspect the building as quickly as possible, but also inspection. Very importantly, in forest monitoring, now there is an X-Prize challenge of $10 million for using multiple drones that need to fly as far as possible and extinguish a fire, personal air vehicles, and space. The new NASA helicopter, planned for 2030, is supposed to fly 10 kilometers instead of 300 meters like Ingenuity. So we need to fly much faster than Ingenuity. Now, let's look at the state-of-the-art on agile flight. So we can plot the state-of-the-art on 2 axes, agility and works that use external sensors like GPS or motion capture systems. So pioneering work was done in 3 research labs, Peter Abil and Andrew Ng lab at Berkeley in 2006, Raffaello D'Andrea and Vijay Kumar in 2010. You may remember some of these videos because they collected more views than Lady Gaga in some cases. They were doing acrobatic maneuvers. Let me show you the one by Raffaello, where the drones are playing tennis. So they showed that the drones are super agile, and that with the appropriate control algorithms you can really unlock their full potential. But they made the assumption that localization was given, which means that you had, a ground truth state of the art, that the state was given. Now, things unfortunately don't go very well when you put the sensors on board. We call it egocentric vision because you see the world from your own perspective. And so when you look at agility, when you put sensors on board, you are not as agile as the works that were using motion capture systems of GPS. So does it mean that you cannot do it? Of course, it's false. You can do it because humans are agile and they don't need motion capture systems. They just use a camera feed. So we want to reach to human level performance and one day maybe go better than humans. So that's the goal of our research lab. Now let's try to go more into the detail and let's start from the basics. I will not show many equations because I'm more interested in giving you the intuition behind, since I know that there is a diverse audience. How does vision-based navigation work? So the minimal theoretical number of cameras that you need is 1. And the minimum number of points that you need to observe to navigate is 1. It was proven by Agostino Martinelli, which was published some years ago. So in general, you have a camera and a computer on board. The camera is oriented to look at some texture in the environment, and you need texture and light. Then the computer extracts some interest points, we call them features, And then the computer builds a map of the environment and localizes it within the map. So it's a simultaneous localization and mapping, abbreviated SLAM, which has been one of the largest research problems in robotics. Why don't you track every single pixel, you may ask? Because then you will need a huge computer. So typically we only focus on features. Okay, so what is the control architecture of a vision-based drone? Well, we have the three classic modules: perception, planning, and control. The perception module is in charge of doing state estimation. It estimates the state that for a drone is the position, the velocity, and the orientation. But perception also does local 3D mapping, very important. Then there is the planning module that takes the output of perception and generates a trajectory, waypoints. And then there is the control module that takes these waypoints and generates the 4 control commands. So we have 4 rotors, so 4 control commands. Okay? Now, what makes vision-based drone navigation difficult compared to ground robots is the fact that planning and control are strongly coupled with perception. I'm going to show you this with a very simple toy example. So why are perception and action tightly coupled? First of all, because you don't have an omnidirectional field of view. You have a camera with a limited field of view. That's the main reason. Suppose that this is our quadcopter, and this is the thrust vector, okay, which is oriented perpendicular to the propeller plane. What is this blue triangle? This is the field of view of the camera, and the camera is looking down, okay? Now assume that the yellow star denotes all the texture present, visible from the drone perspective. So this is basically just one, but you can imagine it's multiple features, and you need to observe those features at all times in order to just hover, okay? So very simple task. But now suppose that you want to reach this goal. Because a quadcopter is under-actuated, it cannot stay in any position. When you tilt, you move. So typically what you want to do is to align your thrust vector with the direction of motion that you desire. But by doing so, you may lose the visibility of the points of interest that you need for state estimation. And now you see why things are actually strongly coupled. Perception and action are strongly coupled. What happens if you lose the visibility of the features? The drone crashes, with huge consequences for safety, public safety as well. So how can we solve this problem? We proposed an idea some years ago called perception-aware planning and control. And now you see why NPC was super useful to solve this. Typically, when you use NPC to control a drone, you have your own state estimator, which is considered like, you know, a black box. But this is actually not correct. Typically, if you assume state estimation to be a black box, then you would only consider the action objectives. So let's do NPC for drone navigation with action objectives. Basically, you want to solve an optimization problem with certain constraints, which is to follow a reference trajectory, to satisfy the under-actuated system dynamics, and to minimize the actuator saturations. These are the typical action objectives of a drone. What we did is that we added the perception objective. We want to keep points of interest always, at least always visible in the field of view, but also we want to minimize motion blur, because if you move too fast, then you cannot identify those features, and then the drone eventually will crash. So how do we do it? Well, if you have already started to map the environment, you can project the environment map into the image, and you can enforce, for example, these points are always visible, so we call this point S, projected in the camera field of view, in the image domain, X and Y coordinates in pixels. And then we want to minimize S dot, which is the optical flow speed, which obviously reduces motion blur. Then we add the quadratic cost to these two, and we add them to the optimization function. And then we used NPC, we use in particular Akados, to solve this at 100 Hertz on board. Now let me show you a simple toy example of how this perception-aware NPC makes a difference. In this scenario, in my lab, we put all the texture in the middle of the room. So there is not much texture outside. Now let's assume that the drone is commanded to go from here to here. So you expect that the drone will fly straight. Does it? Let's look at it. Here you can see the Z plot over X. It's not flying really straight. It's doing a sinusoidal trajectory, more or less. Why? This is the problem of perception-based navigation. The drone is underactuated. When you tilt, the features will move up in the camera field of view. So the drone will not see them. So the perception-aware NPC now will push the drone to go up and gain altitude in order to center them in the field of view. But at the same time, it needs to change its yaw such that while going in this direction, it yaws by 180 degrees in order to look at the textures on the other side. So the movement that emerges automatically is this. Let's see other applications of the perception-aware NPC. Now imagine that you have a gate that you want to pass through. And we are using only the gate for state estimation. So we have a gate detector. If you don't see the gate, the drone doesn't do anything. It collides with the gate. So again, perception-aware NPC, we can do that. And we can do also other things. Now imagine that you want to launch a drone in a new fashion or restabilize after an aggressive flight. So look at my student here. Takes the drone, and now it throws it in the air like a frisbee. And the drone restabilizes itself. Again, it starts mapping the environment, then it takes a waypoint, and the NPC will try to get it in the center of the image and minimize its motion blur, and then stabilize. Okay, so now we understand basically that perception and action are strongly coupled, but this is not enough. This is not enough because the classic perception planning and control pipeline is actually insufficient for agile flight. Why? Because there is imperfect perception and unmodeled effects. When you go very fast, like in drone racing or other things, there is a lot of motion blur that will cause the loss of feature tracks that you need to navigate. But also, often the camera will rotate so quickly that you lose track of points because there is overexposure or underexposure of the light. And then you have a lot of turbulent flow. Because the faster you go, already 5 meters per second is a high speed, you basically fly in your own downwash, and you generate a lot of turbulent flow. And you cannot use CFD, it's too slow. So you need something better. How do humans navigate? Well, humans navigate, of course, with a neural network or a network of subnetworks. So we know that one day we will be able to map sensor inputs to control commands end-to-end, but at the moment there are several problems. First of all, it's very sample inefficient, and even if one day we succeed as a community to make this possible, it will have limited interpretability. So what we have done at my lab over the past few years is trying to improve perception and control by adding or augmenting the classic perception planning and control architecture with the deep networks. But when you start working with deep networks, there are several questions. For example, should we train with or without supervision? How do we get enough training data? Well, as I will show you, we can rely on simulation. Simulation is fast, it's cheap, and it's very safe. But there is a problem. Then there is a simulation to reality gap to address. Rather than talking abstractly, I will focus on 3 tasks that we picked in order to measure the progress of our research with respect to humans. So they are not the most useful, but they are sufficient and necessary to basically measure the progress of research. We picked autonomous drone acrobatics, navigation in the wild, which means in unknown environments, and drone racing. And I explain why each one is very important. But to do this, also we needed to build a very agile drone. So 7 years ago, we started a collaboration with the Swiss drone racing champion, who was 15 years old. And together with him, we built a very agile drone, as agile as the ones that drone racing pilots navigate. Just to give you an idea of the agility, our drone can accelerate from 0 to 100 kilometers per hour in less than a second. A Formula 1 takes 2.6 seconds. It can generate accelerations of up to 5 Gs, which is a lot. We have an onboard computer, an NVIDIA GPU, and then as the eyes we use cameras from Interreal Sense that also come with an IMU, an inertial measurement unit. Now, thanks to the integration of model-based approaches and deep networks, and I'll explain the detail later, we were able to achieve unprecedented agility, and we were able to fly for the first time outside of our lab. On the left, you see our drone doing acrobatic maneuvers, and on the right, flying up to 40 kilometers per hour, even outperforming commercial drones in forest environments and other unknown environments. So we call it navigation in the wild. In particular, what we discovered is that thanks to deep networks integrated with model-based approaches, the networks are much more robust against sensor noise, so missing data, lack of stereo matching, if you know what I mean, than traditional model-based baselines. In addition, they are even faster. They are twice as fast as traditional model-based baselines, so we could fly faster. But to train these networks, we need a lot of data, and you cannot do this in the real world because it would be very long and very unsafe for PhD students. So we resorted to simulation. On the left, you can see the simulator we used earlier for teaching acrobatic maneuvers. And then over the years, we've improved the simulator. Now we are using Unreal Engine, which is a video game engine, and we can realify even more the simulator and make it even more photorealistic or physics realistic if you want. So these algorithms were trained only in simulation and transferred zero shot to the real world. That means that they were not fine-tuned at all in the real world. That means you need a good model of the environment and of the robot. How did we train these neural networks? And what were the neural networks doing? Actually, the neural network was replacing the perception and planning module, but we still kept a traditional model-based controller, an NMPC, to maintain generalizability to unknown drone models. Let me first explain how we train the neural network. We train the neural network with imitation learning, where we imitate an expert, but we didn't want to imitate a human. We wanted to imitate an artificial expert because we wanted to be better than humans. So we took the best model-based planner algorithm that can take very long, but it's okay because we are distilling the knowledge of the expert into a CNN that at inference time will be much slower, actually 10 times slower than the expert. Sorry, 10 times faster than the expert. Now, we train it with privileged information. So the expert has information about the ground truth state of the drone and of the environment. So he knows the position of all the trees and also the ground truth of the drone. While the student neural network at training time only has access to the IMU and to the images. You see, it's asymmetric. With the hope that basically after training, the student will be able to match images to trajectories, although the expert didn't see images, it only saw ground truth. Is it clear? Now the output is trajectories. And then we use an NMPC in order to improve the generalizability to other unknown drone models. Also, again, using a CADOS. Okay, so in the works that I've shown so far, we showed that it is possible to train a neural network in simulation and transfer it to the real world without fine-tuning. We showed that this is possible thanks to privileged imitation learning. But there are other tasks where you don't have an expert. You don't have an artificial expert. And this is the case of drone racing. There is no artificial expert. I'll try to convince you. Let me show you drone racing. Who has ever seen live a drone racing competition? Raise your hand if you did. Only one, two. Okay, good. Now I'm going to show you a video. This is Marvin, 15 years old at the time of the video.
Get ready on the top in less than 5.
So, drone racing is a very, very difficult sport. You are pushing the platform to the limits of physics. It's mostly bang bang. That's the way I navigate it. As you can see, Marvin always cuts the gates, close to the edges of the gates, because you want to minimize the lap time. That's the only way to win the race. So you want to minimize non-differentiable objectives. That's the key that we are going to talk about later. It requires quick decision thinking. As I told you, the latency of expert human pilots, like Marvin, is 250 milliseconds, but humans learn to compensate for that. Very important. Another thing that human learns is the battery voltage drops significantly, especially when you accelerate a lot. So you need to also learn that. It requires a lot of expertise, so it requires days to weeks for a specific track. So in drone racing, humans are overfitting the racing track. Very important. They know it in advance, like in Formula 1. You know it for years. And so they do the same in drone racing. Sometimes they even receive a CAD file with the racing track in advance so that they can practice on their drone racing simulator. So how do we formalize the drone racing problem from an optimal control perspective? It's the problem to find the control inputs U of t that minimize the time, the flight time, through a series of gates. So the organizers define the order of the gates. So you know which ones have to be passed, in which order they have to be passed through. Okay, that's very important. We know this in advance. From an optimal control perspective, you want to generate these control inputs subject to different constraints or objectives. System dynamics, input constraints, state constraints, physical constraints, but most importantly, perception constraints. Remember what I told you before. You now need to find trajectories or control inputs that facilitate perception, because you're using your own images for destination, so you want to guarantee the visibility of the points of interest, and you want to minimize motion blur. So it's very, very difficult to generate trajectories. So when we started working on this problem 7 years ago, we started by making assumptions. So let's start assuming that the state is known. So we have an oracle called the motion capture system that provides the state at all times, which of course is not true. But we also have a motion capture system in the lab, and we built an arena of 30 by 30 meters, thanks to the ERC money, to do that, with a motion capture system of 40 cameras. So we have it. We can ground truth everything. So let's assume the state is known. How would you solve the drone racing problem? Because the map of the gates is known in advance, you can split the problem into planning and control. So first you generate a time-optimal trajectory, assuming your model of the environment and of the drone, and then you try to track this trajectory. And that's what we did. Look at the video. You start with the initial guess, and this is an algorithm that does numerical optimization, nonlinear numerical optimization, and converges towards the optimum using the real quadruple model, okay, identified with system ID. So this is ideally the truly time-optimal trajectory, truly time-optimal with some quotes. But there is a pros and cons. The pro is that this algorithm allows you to find a true minimum lap time. So it provides a lower bound on lap time. But there is a problem. First of all, the optimization takes 1 hour. And this trajectory is optimal as long as you can stay on the trajectory. Can you stay on the trajectory? No. Because there are turbulences. The air is chaotic. You cannot stay on the trajectory. And remember, we are still even assuming motion capture. So by the moment you deviate by a few centimeters, in principle, you need to replan the trajectory. So you need to make this algorithm faster. So 1 hour. So you can think that it got us quite busy. So another PhD student then proposed the following. What if we do not generate the truly time-optimal reference trajectory, but rather we generate an approximate trajectory with a simple algorithm that assumes that we don't have the actual quadruple model, but that we model the drone as a point mass. Then in this case, the trajectory generation takes less than 1 millisecond. And then we use an NMPC, Model Predictive Control, again, solved with a CADOS on board at 100 Hertz. What do we do in a contouring control? Now, we are not tracking anymore a time trajectory, but we are tracking a 3-dimensional path, but loosely. So we want to minimize the contouring error to the 3D path, while maximizing the progress towards the next gate. So we are trading off accuracy for for progress, similar to what Formula One pilots do. So we have these two terms, and we were able to do amazing things. We are able now to replan on board with less than 2 milliseconds, for faster than real time. And we can do amazing things. Here, for example, we are disturbing the drone with wind up to 70 kilometers per hour. Okay? Then what you're going to see now is my PhD student that is going to move the gates. Of course, he's wearing a helmet, just in case the drone crashes against his. And so the drone is capable to replan even with the changes in the environment. Great. So we are able to replan. But was it able to outperform the world champions? No, not at all. It's not enough. So even though now we are less relying on the reference trajectory, we still are inferior to human performance in the face of modeled effects and modeled uncertainty. So this was not enough. And remember, here we were cheating. We were using a motion capture system that provides ground truth state at 400 times per second, which is impossible in the real world. It's not egocentric. So, at the same time, another PhD student was working on RL, Yulong Song. And RL has, as it was been already pointed out several times in this conference, has several benefits. But let's try to understand now what happens when you try to solve drone racing from the perception perspective. Why is perception so difficult? Now you're going to see what the drone sees from its own perspective. The drone has a 160 degrees field of view camera, the same camera used by expert human pilots. And then we have a gate detector that detects the gates at 30 hertz. I don't know if you can even follow the video, it's so fast. Now let's apply computer vision, the state-of-the-art computer vision. You can detect a gate, and from the four corners of the gate, because you know their 3D position, you can triangulate the position of the drone and its orientation. This is state-of-the-art algorithm. Great. So does it mean that now we know the state? Yes. But what about the covariance? This is the key difference between egocentric vision and ground truth state. Ground truth state estimation provides a state with a very small error, 1 cubic millimeter. When you use egocentric vision, look at the covariance, it grows and shrinks. Why? Because there is the famous parallax effect. With a camera, with a single eye, it's difficult to estimate distances from far away objects. It's easier from close by objects. What is the error as a function of the distance? It's quadratic. Usually we have an error that can go up to 2 meters or more, depending on the relative distance from the objects, 2 meters. So you need to be able to cope with this varying state uncertainty. And it's just one of the sources of the errors. There is another big source of errors, which is systematic errors. The drone is not a rigid system, it's soft. The camera plane moves with respect to the rotor plane because there are dampers to isolate the vibrations from the motors to the camera. So they move relatively by 1 centimeter on each axis. This 1 centimeter relative motion can cause errors in the estimation of up to 2 meters again. And they're very difficult to model. So Yulong was the other student, then developed a neural network controller, actually a simple 2-layer MLP, that is now trained via model-free deep reinforcement learning. And this trained mostly in simulation, mostly. I'm going to get on this point later. The RL optimizes a non-differentiable objectives. There are 4 terms, but 2 are non-differentiable. The progress, you want to maximize the progress towards the finish line, and then you want to penalize crashes, collisions against the gates and the environment. If you just work with these 2, it doesn't converge within reasonable time. So we had to guide the training process by adding 2 other terms. A perception term that guides the training process by rewarding policies that are favorable to state estimation. So by, for example, forcing the drone to face the camera as long as possible towards the next gate. And we also added a smoothness term that avoids kind of, shaky behavior. So let me now run the training that was done in simulation with a time lapse. The training takes about an hour, and now you're going to see it in 10 seconds. We have 100 drones that are learning to fly from scratch. Actually, they're learning to race from scratch. Each yellow line is a flight attempt. We have 25 million time steps. The training time is the equivalent of flying one single drone for 60 days without any interruption, 24/7. But it takes only 1 hour. Less than the time it takes an expert drone pilot to win a race. Now, interestingly, it only takes 10% of the interactions with the environment to learn to fly fast. That's why we are not just flying fast, we are racing. But it takes 90% of the time of training to fly like a world champion pilot. And this is very interesting because we can make an analogy to how humans learn to walk and then run. It takes 1 year to learn to walk. It takes many more years to learn to run, and many more years to run like, a sprint champion. So after 7 years of work, we decided to invite to Zurich the world champion drone racing pilots. Since there are 2 drone racing leagues, we invited the champions of each league, Vanover and Bill Matta, and we also invited Marvin from Switzerland. Important is both the human drone and the AI drone were identical. Same mass, same aerodynamics, same camera, same field of view. The only difference was that one had a computer on board and the other one had the brain off board. Let me show you the footage of the race. So the AI won, of course, otherwise I wouldn't be here telling you the story. How much was the difference between the AI and the best human pilot? It was at 0.5 seconds. Is this a lot? It is significant, because in these competitions, the difference between first and second is 0.1 seconds. Here you see the lap times distribution over 1,200 trajectories, all released open source, and there is also a competition for users. Lap time versus different pilots, including Swift is our AI drone. So Swift obviously demonstrates the smallest lap time. There is a distribution due to battery, chaos of the air and everything. Vanover is the second one. Bitmata is the third. Look at Marvin, the Swiss pilot. You know there is a difference between local champion and world champion, obviously. The results were published in Nature and Science Robotics, and I was happy that the first author was also appointed this year the European PhD Award on Systems and Control at ECC. So thanks to you, the reviewers. However, differently from the previous examples, it was not enough to train in simulation for beating the world champion, because simulation has a limited knowledge of the real world and of the system. As you can see, there is an error between sim and real of up to 2 meters. And most of this error comes from aerodynamic effects, the famous vortices I was telling you about at the very beginning. You cannot use CFD, because CFD requires a lot of time and is specific for a trajectory, so you cannot use it in replanning. So what we do is that, again, we use a neural network to model the residual forces between first principle models using finite element theory and ground truth. By capturing these residual models, and we then model them with a neural network, we improve the simulator, we fine-tune the policy in simulation, and then finally we transfer it to the real world, all vision-based, no cheating anymore. So we do simulation to real. The first real is with a motion capture to capture the residual model. Then we use this model to fine-tune the policies in the new simulator, and then we deploy vision-based without motion capture on the real world. So this is the first takeaway of this research. The second takeaway of this research is that RL beats optimal control for racing, robot racing, at the current state of the art, but in racing, okay, not in general. Still, optimal control is good at generalizing, but why? Well, the first reason is what also many of you said during the previous days. It directly optimizes a non-differentiable objective that is very sparse, lap time, while NPC requires a continuous differentiable objective. But there is another reason. Because optimal control decomposes the problem into planning and control. So it uses a trajectory as an intermediate representation. This trajectory biases the set of possible behaviors in preventing exploration. So RL is able to explore. Also, RL exploits domain randomization, exposing the controller to a set of behaviors that he can actually discover, making the control maneuvers much more robust. So, outlook, and then I'm done. What are we also looking at? I have a lot of more slides. Also, why the AI won. If you're interested, I can show it in the question session. So, we know that RL outperforms optimal control in racing, but it lacks safety. So, one paper that tries to go beyond this was published at IFAC this year. And it comes from the following observation. Let's take the case of tracking a reference trajectory with NPC. Basically, this is the optimization function that you want to optimize. And when you expand it, it can be converted to a quadratic program. Now, the observation that we made was that for real-time performance, the optimization problem is often converted into a quadratic program that has the following shape, as you may know. So, my PhD student Angel made the following observation. The problem is that often the issue we are facing is that we have to appropriately choose the terms Q and P for every different task. So the question that he had is, can we directly learn the terms Q and P using RL instead of using a reference trajectory or complicated contour control formulations? So this is what the typical RL training framework looks like. You have the critic and you have the actor. For us, the actor is an NLP that maps observations, the state, to control commands. And Angel thought, can we benefit RL with NMPC? So instead of learning directly the control commands, we want to learn a mapping function that goes from observations to Q and P. So now Q and P are learned via RL by trying to maximize this reward function, with the hope that then the results will be able to benefit from both the exploration capability of RL and also the safety guarantees of NPC. He calls this actor critic NPC, and what we showed in the paper that now is about to submit to Transactions of Robotics is that we are able to achieve the same lap times and robustness as reinforcement learning. But all this work was still using state estimation from an onboard camera. Human pilots do not do state estimation. Human pilots go from pixels to control commands. So another paper that just came out tried to answer the question, can we fly from pixels without explicit state estimation? Yes, finally we can do it. Again with RL. On the left you see the evolution of training of state-based RL, and on the right, on the left you see state-based RL, and on the right you see pixel-based RL. The pixel-based RL takes longer, but eventually converges to the same performance as state-based RL, but it takes almost 20 times more iterations. So instead of 1 hour, it takes 20 hours. And so with this, I would like to conclude this talk. So where are we? We are still very far from human pilot performance. There's still a lot of work to do, and thanks a lot for your attention.
Yeah, thanks a lot for your amazing talk, Davide. Yeah, so we are already a bit ahead of time, but I would like to allow for some questions. Are there any?
A lot of information to digest, maybe.
A lot of information. Yeah, okay.
Yes. Yeah, sure.
I know nothing about this.
Okay.
For the, like the world champion, what is the communication time between the onboard camera and the VR?
10 milliseconds, so it's negligible.
Okay.
And they learn to compensate for that. The majority of the latencies comes from the brain, especially the behavioral latency, by the nervous system from the brain to the fingers. Yeah.
Thank you very much for this amazing talk. It was really impressive also to see everything from high level, and as a scientist and a researcher and professor, combining all this stuff together and having this amazing, impressive storyline is really inspiring. I have a question, slide 31. Yes, here. So the second approach here, did I understand it correctly? Are you taking actually the pre-optimized trajectory from one?
No, we are not.
Okay.
Because that one takes too long. So we use an approximation of that, assume that the drone is a point mass, so that takes a fraction of milliseconds. And so we loosely track this reference trajectory, but it still is a reference. That's the problem.
Okay.
So RL doesn't have this, even if it's a loose trajectory to follow.
What about combining both? Like the thing here, when we go to one gate, it like I think if I compare it to a drone racer, the drone racer tries to capture a certain entrance to the gate so that he wins time for the next gate as well. So and that makes like the long global trajectory planning better. What about taking the first one, like this global trajectory, and then making a local replanner?
Yes, I see your point, and that's why also RL is also, because it uses the all global knowledge, while NPC is more receding horizon. But the problem that is, what we were doing before was exactly trajectory NPC. So we were tracking this optimal trajectory with the NPC. But the problem is that this optimal trajectory only is generated with a non-accurate model of the environment of the robot. So it's not capable to discover new behaviors, because actually they can only be discovered, when you react with the environment. And that's the one thing that probably shows you why. RL wins because can discover maneuvers that the standard one cannot. Not even the human. The human is in red, the AI is in blue. This is the most difficult maneuver. It's called split S. You have to go through the top gate, then make a 180-degree turn, so you traverse the top gate blindly, but you start orienting the camera, which is the one, the triangle in blue, such that by the moment you have traversed the top gate, you are already looking down at the bottom gate. Humans do this maneuver too early, while the AI learns to do it a little bit later. So we're talking only a fraction of a second, but it's enough to basically determine the win or loss of a competition. So that's why truly the optimal trajectory is actually not real-time optimal, because it's only computed with a certain model of the environment. By the way, it doesn't have this sophisticated turbulent flow, dynamics, because it's too slow to run it. And also it doesn't have a perfect model of the drone, which changes. Also the battery model, very difficult to model. RL was not exposed to the battery model, but it was still able to actually generalize to unseen batteries.
Thank you.
Yeah. Davide, I also have a question concerning the constraints. So I assume you have the gates in the constraints. Mm-hmm. Do you put uncertainty on that, like some safety margin, or?
Good question. So in the Nature paper, what we do is that we jitter, so we expose the AI to domain randomization of the state. So we add in simulation Gaussian noise to both the state and the position of the gates. We jitter the gates with a variance of 10 centimeters on each corner. So 3 sigma equal half a meter, more or less. Okay? That's what we do. Yeah, we need some domain randomization, because otherwise it won't be able to cope with uncertainty in the placing of the gates, right?
Yeah, okay. Moritz?
I also enjoyed the talk. I have a question about this differentiable NPC. What you said you solve a QP, so what is exactly solved in what model? I mean, this F, is what do you
the actor critic NPC.
Outlook.
Here, this one.
Yes.
So basically we assume that any problem of drone racing or agile navigation can be converted into this quadratic problem. The problem that we face is always tuning the other parameters of this cost function. It takes ages, okay? So the question is, can we learn that?
My question is about the f, the little f that you have there. So
the f is still the dynamic model of the drone, so we assume it to be known. So we use the prior of the model. Yeah, we use the model of the drone. That's our f.
But is it a nonlinear or linear model? I mean, what software is used for the QP and how do you, I mean...
That is the classic dynamic system of the drone, of a quadrotor, which of course is not perfect. So the assumption here is that the QP will be actually compensating for these inaccuracies in the dynamic model. Okay? The residual. So they incorporate implicitly the residual.
And what QP solver is used?
What QP solver is used? Yes. Oh, this is in the paper. I think it's always a Katos, I think.
Okay, so then it's maybe an NLP.
Yes.
Or successive QPs. Okay,
yeah.
Thank you. Oh, sorry.
This is very technical now.
My question is also related to this. Why would you like to learn in the discrete time formulation rather than the continuous time formulation where you would have fewer parameters?
Okay, this I'm not sure, okay, because this is a little bit outside of my expert domain. It's more like my PhD student. So we always use the discrete domain in all our research, okay? Sorry.
Okay. Yeah, I think unfortunately we have to come to the end. So thank you very much again, Davide.
You're welcome.